Yes. Your next quiz, I would like it to be Thursday. Quiz on hydrolysis and mixtures of strong acids and bases, which we're finishing off today. Can we do that? Okay. I mean, I can put it on Friday. It's just you're just pushing it out a day. What's that? Okay, we're going to vote. Would we like it on Thursday? 1, 2, 3, or Friday? I guess we're doing it on Friday. Now, if you would like to do it on Thursday, you can certainly do it then, okay, if you would like to. No problem. The lesson will, of course, be recorded as per usual. So if you're like, I just want to get it out of the way because I have other stuff going on Friday or whatever it is, let me know ahead of time so I can make sure the quiz is ready and printed. Otherwise, I might forget to print it. Okay? All right, so Quiz Friday on sections 5.3 and 5.4. Okay, 5.3, 5.4, hydrolysis and mixtures of strong acids, strong bases. 3, 5.4. Hydrolysis. Mix of acid plus base. Okay. So today we are going to look at mixtures of strong acids and strong bases part 2. And there's really not actually that much more to part 2 than there was to part 1. The only thing is we'll be dealing with some acids and some bases which have more than one proton or more than one hydroxide. Okay? Last time we dealt only with like HCl and NaOH, one of each. But basically it's just you calculate your moles of hydrogen from your acid and you calculate your moles of hydroxide from your base. And then you determine who is the limiting reactant, who is the excess reactant. And then you check your moles of H and OH in excess using a RICFA table. Use the net ionic equation. And if this is a net ionic equation for a strong acid plus a strong base, what is the net ionic reaction for a strong acid plus a strong base? H plus plus OH minus goes to H2O. Yeah. Okay. If you don't want to use a RICFA table, you do not have to. You can find the amount left over any way you want to, but as long as you get it correct, that's good. And then you will take whatever your moles that are in excess and divide by the total volume, and from there you can go and you can find your pH. So let's find the final pH when 50 milliliters of 0.2 molar HCl are mixed with 50 milliliters of 0.3 molar barium hydroxide. And you might think to yourself, who's in excess? Let's find out. Okay, we have our formula equation, which is HCl plus BaOH2 gives BaCl plus H2O. We balance it with a 2 here and a 2 here. And then we complete ionic equation it, split everything up because they're all strong. They all split up into ions except for the water, which is a liquid. And then, of course, our bariums cancel, our chlorides cancel, and we're left with 2H plus 2OH gives 2H2O, and then we simplify it and we get H plus OH gives H2O. This is the net ionic equation for all strong acid, strong base neutralization. Calculate moles of H. So you're going to take your 50 milliliters. Remember, what does of mean? Of means times. So 50 milliliters times 0.2 moles per liter times 1 mole of H plus per 1 mole of HCl. That gives us 10. Oh, and look, I did not change that to liters. So will I be finding moles or will I be finding millimoles? I'll be finding millimoles. If you feel uncomfortable with that and you want to leave it as liters and do regular moles, that's totally fine. Okay, but look what a nice number you get. 10, such a nice number. 10 millimoles of H plus. Let's calculate our moles of OH minus. 50 milliliters, liters cancel out. Moles of BaOH2. Now this is where the stoichiometry gets interesting because there are 2 moles of OH in every BaOH2. So we have to multiply everything by 2 and we get 30 millimoles of OH. And at that point, you should be able to say, who is the limiting reactant, H or OH? H is the limiting reactant, and OH is the excess. So we are going to use up all of the H. So we're going to do our RICFA table, where we have our reaction, but because it is going to completion, we're not going to have an E at the end, we're going to have an F for final rather than an E for equilibrium. Okay? And there is our initial line there, and we ran out of space, so now we're going to put in our change, and because we're going to use up all of this, that's going to be our change. Our change is going to be 10 millimoles. Okay, and you'll notice over here, I've put millimoles there so I know what unit I'm dealing with. Okay, so here's our limiting reactant. We use it all up. So these two numbers should be the same for your limiting reactant, what you start with and what gets used up, because it all gets used up. And then because this is a 1, whoa, that was supposed to be a pen, not a highlighter. Because this is a 1-to-1 reaction, this will also be 10. You can fill in the water column, but is it necessary? No. So up to you. Optional. Because it is a liquid. Okay, and then our final moles are 30 minus 10 is 20. So 20 millimoles of OH minus are in excess, left over. So that's what we have now in our solution, 20 millimoles of OH. So we put our millimoles of OH divided by what volume do we need to use? The total volume, and because we used millimoles, we're going to use milliliters. Okay, so we got our milli and we got our milli. Those will cancel out. And our total volume is 50 plus 50 gives us 100 because we have mixed the two and we get 0.2 molar OH minus. Yes? So we could at that point turn that into concentration of H plus, and we could find then pH, or we could turn it into POH and find pH. Any of those will do. Okay? We have some exercises here. We're going to leave those just for now because we get to go on to the exciting part of this unit here, which is on page 66. So we are going to look at mixtures of a weak acid, and a strong base, SB. Now, before we do anything, Actually, yeah. No, we can write it down here because we have a place for it. We have our weak acid, which we're going to call W. Or no. Yeah, no, I'm going to do it up here. Sorry. Keep changing my mind. Plus XOH. That is our weak acid. That is our strong base. Am I going to have an equilibrium arrow here or a one-way arrow? Tell your partner, what do you think? So you guys are going to show me, you're going to show me either one-way arrow or equilibrium arrow. One way or equilibrium? One way. Why not equilibrium? Because you've got a strong base. Only one of those reactants needs to be strong to push it all the way to completion. Okay? Yes. You can't do that. No, it doesn't happen. Yeah? Okay, and so you would end up with XA plus H2O. Anyway, that doesn't really matter. The only point I wanted to make there is that because one of the members of that pair is strong, it will go to completion. This is the kind of thing that takes place during a titration. Okay. Yes, we can also get the strong acid, strong base. That can take place during a titration as well. Okay. But this one, when a weak acid is partially neutralized and we are before the equivalence point, because when we hit the equivalence point, the acid is completely neutralized, yes? And after that, we're going to have excess base. So when a weak acid is partially neutralized, which species is in excess? So if I have my weak acid and my strong base, and I have only partially, if I've added enough strong base that I've only partially neutralized the weak acid. Here's my weak acid, yes? I'm going to be all the base because there's only one of me, okay? Strong base, second strong base particle, partially reacted. So I only added 2 strong base particles, yeah? And they reacted with 2 of the weak acid particles. Who's in excess right now? The weak acid. I would need to add 2 more strong base particles to completely react it. And then after that, I would need to add more strong base to go past the equivalence point. Okay? So before the equivalence point, we are going to have weak acid is in excess. So we're going to calculate the pH when 2 milliliters of 1 molar NaOH is added to 8 milliliters of 1 molar weak acid. So let us write our formula equation. Okay, our formula equation, we've got NaOH plus CH3, COOH, goes to, and who are our products? Na, CH3COO, plus water. Okay. Complete ionic equation. Can you guys write the complete ionic equation for this? Good gosh, there's hardly enough room on there, is there? I should have started further to the left. Did you leave your acetic acid together? It is a weak acid, so it is mostly together. Weak acids are mostly together. All right, and then we get rid of our spectator ions, and we are left with Na goes away, and that's it. Okay, so we have OH minus plus CH3, COOH. Oops, this should have been an arrow up here. Whoopsie. There we go, that's an arrow. Goes to CH3COO minus plus H2O, and there we go. And now we are going to do a rice table. A RICFA table. Sorry, yes, a RICFA table, not a rice table because this is going to completion. So in order to do our RICFA table, what do we need to calculate? We need to calculate the initial moles of OH. Okay, so did I put it in here? Oh. So our initial moles of NaOH (2 milliliters) times 1.00 moles per liter is how many millimoles? 2 millimoles. And we're going to play fast and loose with our sig figs, okay? Because we just want to put a 2 in there so it's easy. Yes? So in our table, we're just going to put 2. What? This should have said OH minus. Oh, no, we're okay. Sorry. All right, and then how much CH3COOH do we have? CH3COOH equals 8 millimoles. Are we okay without showing all the work out perfectly? Okay, so we have 8 millimoles here. And this is a 1 to 1 to 1. And how much CH3COO minus do we have to start with? 0. Okay, and the water we don't care about. What is our change going to be? Change is going to be -2 because we use up all of our limiting reactant. Use it all up. Okay, and that's going to be -2, and that's going to be +2. So we end up with 0 and 6 and 2 millimoles. So our new concentration of the acetic acid is 6 millimoles over how many milliliters? We got 2 milliliters and 8 milliliters is 10 milliliters. Yes, total volume. 10 milliliters is 0.6 molar. Our new concentration of the acetate ion is, let's see, how many millimoles did we have of that? We had 2 millimoles. And that is in 10 milliliters. Yeah, millis cancel, and we get 0.2 molar. And now I have an acid and I have its conjugate base. Yes? Those form what with each other? Those form an equilibrium. So what we're going to do is we're going to write down, you can actually use either the weak acid equilibrium or the weak base equilibrium. It does not matter. You'll end up with the same pH at the end. Because it's just easier to do acids than bases because we have all the Ka's on a table, let's go with the weak acid equilibrium. Okay, so here's our weak acid equilibrium. We have CH3, COOH plus H2O in equilibrium with CH3, COO minus plus H3O plus. So basically what's happening is we're having partial neutralization. We end up with some species, and then they set up an equilibrium with each other. Okay, so we have a reaction that goes to completion, and then the products of that reaction, well, one of them is a product and one of them is a reactant. But we still have reactant left over. They form an equilibrium with one another. And our initial concentrations are 0.6 and 0.2, and water doesn't matter. And what's the initial concentration of hydronium? Zero. Which way does this equilibrium have to shift? Has to shift to the right because we've got something at 0, right? Okay, so we got plus, plus, minus, x, x, x. So 0.6 minus x, 0.2 plus x, and x. And then at this point, it becomes a matter of using your Ka, and we look at this and we're like, oh, this looks yucky. This would give me a quadratic, yes? I would end up with an x squared term and an x term and la la la. How do we deal with that if we don't want to have a quadratic? We're going to assume x is insignificant. So here and here, we are going to assume that X is less than 0.2 or 0.4, or you can say assume X is insignificant. Because, or sorry, it should say and less than points, it should be 0.6. Yeah, sorry about that. X. Okay. And then at this point, we just solve for X. Blah, 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 blah. We get X is equal to 2.4 times 10 to the negative 5, and we get the pH is 4.27. Okay? And that's kind of as gross as the calculations in this unit get. Yeah? Because you've had to do a neutralization, but it didn't go all the way to completion, so you had to figure out who's in excess, by how much, and then you had to do a Rice table, right? So this is pretty gross. You would never get anything like this on the regular test. You might on AP, but I think it's probably unlikely because that's a big, bad calculation. But definitely in university you'll get this, so is it worthwhile having seen it? Yes. Also, it's going to help you understand titrations, because before you hit the equivalence point in a strong acid, or sorry, a weak acid, strong base titration, you can see that the pH is going to be somewhat acidic. Yeah? Which kind of makes sense, right? Now, we have something special that happens when exactly half of the weak acid is neutralized. When exactly half of the weak acid is neutralized, which we call the half equivalence point, and you can see that's going to happen because we have the same concentration for both of these things, but we only have 2 milliliters of base, and we have 4 milliliters of the acid. And if you do your calculation here, we have 2 milliliters times 1 mole per liter gives us 2 millimoles, and here we have 4 milliliters times 1 mole per liter gives us 4 millimoles. Yes? So you can see these 2 millimoles are going to neutralize half of that. Yes? Okay, so let's chuck these in a RICFA table, because this is our strong base with our weak acid. We have 2 millimoles, and we have 4 millimoles. Oops, I should have made that blue, but that's okay. And who gets all used up? The 2. Okay, so we use 2, and these have to be the same, and we're making 2 of these. So we end up with 0 of the OH. We end up with 2 millimoles of the weak acid, and we end up with 2 millimoles of the conjugate base. Yeah? So you've got equal moles. That's the whole point. At the half equivalence point, you have equal moles of acid and conjugate base. And something magical happens then. Kind of a little bit like what happened when we had exactly the same amount of the indicator, the acid form of the indicator, and the base form of the indicator. Here we've got the acid form of the acid and the base form of the acid, okay? So we have equal moles of the acid and the conjugate base. That means their concentrations will also be equal. Okay, these two are equal. And so that is 2 millimoles in a total volume of 6 milliliters. 2 and 6, 2 and 6, that gives us 0.33, 0.33. Huh? Are we okay here? Okay. And we've got our weak acid equilibrium. This time I did not use water. I just did the dissociation. Okay, so we have 0.33 moles of the acid form. 0.33 molar. Remember, these are now concentrations, molar. And this is a Rice table. So that's our equilibrium concentration. And we have our base here. And we have to shift to the right because we don't have any hydrogen. So these are going to go up by X. This one's going to go down by X. And what are we going to do to make our lives easier? We're going to assume these X's are insignificant. So what we end up with is this is our concentration of A minus here. Whoa. Ay, ay, ay. And this is our concentration of HA. And they are the same. Okay, because even though we went up and down by X, it's not enough to make a difference to the concentrations, so they are just the same. So, if they are the same, what happens to them? They cancel out, and you're left with X is equal to 1.8 times 10 to the minus 5, and let's remind ourselves, this right here, X is, what did X equal? X is the concentration of hydrogen, and what's this value over here? Ka. So at the half equivalence point, Ka is equal to concentration of H plus. So if you do your titration and you measure the pH all the way along and you graph it, right? Let's say you measure your pH all the way along during your titration and it goes up, 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 and you're going to learn later on that when it hits the equivalence point, it does this. Okay, so you'll recognize later that that is the equivalence point. You can actually calculate if this is 10 milliliters, then the half equivalence point would be 5 milliliters. Yeah. And you can look up there and you can say, what is my pH? And from there, if you know the pH, you know the H. And if you know the H, you know the hydrogen. And if you know the hydrogen, you have now found the Ka of the acid. So that is one method of finding the Ka of, like, say, an unknown acid, is to do a titration, plot the points. Don't worry if you're like, titration, plot points, what's happening? We will get to all of that and do it in more depth later. Right now, you just need to know when you're at the half equivalence point, when you've neutralized half of it, Ka is equal to H plus. That's your homework. That's hydrolysis. Okay? And that's going to be on your quiz on Friday. Or Thursday if you want it.